Hi everybody, in this video we're going to learn an alternative way to balancing oxidation reduction reactions. The method we showed in the previous video is typically referred to as the half-cell method, where you take a redox reaction and divided it into the two half reactions, the oxidation and the reduction. The method that this video is going to show you is what is often referred to as the oxidation state change method. And the advantage of this second method is that you're going to find that it takes up a lot less space, that you can kind of get to a balanced reaction a lot more quickly. This is probably going to be the method we would encourage you to use if you're ever asked to balance a reaction in the context of a multiple choice question. Now, the half reaction method, the first method we showed you, definitely has its advantages in that it provides a little bit more detail about what's going on in each of the half reactions, the oxidation and the reduction. And those details will come back to being important when we start to talk about galvanic cells in some later on videos, in fact, probably coming up next. But let's zero in on what we're talking about here. So we have this overall redox reaction that involves bromide turning into bromine and permanganate turning into manganese 2. And so we need to go ahead and balance this reaction. And just like before, when we balance redox reactions, at the end, the number of atoms of all types on both sides of the arrow have to be balanced, as well as the net charge on the reactant and product side. All right, in this algorithm, and I'll go through somewhat slowly in this first example so you can write down the steps. Step one is to assign oxidation states. So there's step one. Let's go ahead and start doing that. So we have here bromide, so that has a -1 oxidation state, obviously. Actually, I'm going to make my marker just be a little bit smaller. So we have a -1 oxidation state. Then we have the permanganate, and I'm going to zero in on the manganese. I know that's going to have a +7 oxidation state, because ultimately I'm only going to care about those things whose oxidation state changes. The elemental bromine here has an oxidation state of 0, and of course the manganese 2 ion has a oxidation state of +2. All right, so then at this point, what I want to do is I want to take a look at anything whose oxidation state changed, in this case the bromine and the manganese, and make sure that those things are sort of what I like to call pre-balanced first. So for example, I have one manganese here, one manganese there, so the MNs are good. But the bromines, I have 2 on the product side, and right now only 1 on the reactant side. So I'm going to go ahead and put a 2 right there for now. That coefficient might change later on, but I need to make sure that the elements whose oxidation state changes are set to balance first by putting in the appropriate coefficients if needed. All right, so now what I do is I kind of track the change of my electrons. So let's start here with the bromine. So the bromine goes from -1 over to 0, and I like to draw lines connecting things that are changing oxidation state. And the manganese is going from +7 here over to +2. All right, so now let's write out the details, because remember, eventually the number of electrons swapped has to be the same. So here's how I write this. I have one manganese atom, 1 Mn, and it changes by, it goes from +7 to +2. That is a change of 5 electrons. And then I'm going to leave a space here because I'm going to multiply that 1 times 5 by a multiplier such that my electrons coming and going and the oxidation reduction will be the same. So I do a similar kind of calculation here for the bromine. The bromine goes from -1 to 0, so that is 2 bromine atoms, and I am exchanging their 1 electron, right? So it goes from -1 to 0, so I'm exchanging 1 electron, and then this is going to need to be multiplied by an appropriate multiplier. So what do I have here? I'm in the process of exchanging 2 electrons for bromine and 5 electrons for the manganese. So in order for the electrons to balance out, I'm going to need to multiply my bromine by 5 electrons, or do it essentially 5 times, and I'm going to need to multiply my manganese by 2 and do that reaction twice. So these numbers I've just put into these blanks, they become my coefficients in my balanced reaction. So I take that 2 and I put the 2 in front of both of the manganeses, and I take my 5 and I put that in front of my bromines. So I'll have a 5 here, and now this 2, I have to multiply that by 5. That now becomes 10. All right, so the atoms whose oxidation state changes are now balanced, as are the number of electrons. The key idea being here, right, we have 10 electrons right there going into the reduction, and of course I have 10 electrons here coming out of the oxidation. All right, so now we have to go ahead and balance things like the rest of the charge and the O's and the H's. So we're never going to put electrons into this method. We're going to kind of skip over that step. The way I'm going to balance charge is by putting in the appropriate ion, either H plus or OH minus, depending upon what conditions I'm under. Now this reaction is going to be balanced under acidic conditions, and so that means I get to put in H pluses. So the question becomes, which side, the left or the right, do I need to put in H plus to get the charge on both sides to be balanced? So let's see what I have. I have 10 minus and 2 minus, so that is a total of 12 minus on the left. On the right-hand side, I have 4 plus. So then where do I have to put the H pluses to balance charge? Clearly on the left-hand side. And how many of them am I going to need? Well, a little bit of quick math here. It's going to be 16 H pluses have to go on to the left-hand side. So now my charge is 16 plus minus 10, so I've got 6 plus minus 2, so 4 plus overall. That matches my 4 plus on the right. Now when I added the H pluses, of course, I probably also messed up the balancing of the H's. And so what do I need to do to fix the H's? Well, you can see here I have 16 H's on the left, no H's on the right. So to fix that, I'm going to go ahead and put in the 8 H2O's on the right, because remember this is aqueous chemistry, so water is readily available. So then this should have taken care of my H's. 16 H's, 8 times 2 is 16 H's. Now at this point, everything should be good, because the elements whose oxidation state changed got balanced. The number of electrons coming and going was balanced. My charge got balanced, and my H's got balanced. The only thing I haven't overtly paid attention to has been the oxygens. But if all of those other factors associated with the reaction are balanced, then the O should fall right into place. And let's take a look. What do I have here on the left? I have, here we go, 8 O's on the left, and I have 8 O's on the right. So this reaction should be fully balanced. Let's just double check. 10 BRs, 10 BRs, 2 MNs, 2 MNs, 8 O's, 8 O's, 16 H's, 16 H's, and of course the charge. 16 minus 10 minus 2 is 4 plus, and 2 times 2 is 4 plus. So this reaction, I know with confidence, is fully balanced. All right, so this took up probably a little less space than what it takes to do the half reaction method that we showed you before. All right, let's do this a second time, and we'll zero in on balancing something under basic conditions. Now, let's see if we can go through this one a little bit more quickly. Hopefully, we are somewhat comfortable with the method here. All right, so my oxidation states, I have plus 3 for this nitrogen, 0 for the aluminum, minus 3 for that nitrogen, and plus 3 for that aluminum. Okay, my aluminums go from 0 to plus 3, and my nitrogens go from plus 3 to minus 3. And my nitrogens, there's 1 there, 1 there, my aluminum's 1 there, 1 there. So I don't have to put in any temporary coefficients in front of anything. So then, let's see, I have 1 aluminum atom. It is changing by 3 electrons, and I'm going to multiply that by something in a moment. I have 1 nitrogen atom. It changes by a whopping 6 electrons, and I'm going to need to multiply that by something in a moment. So what do I have here? I have 3 electrons going out of the oxidation. I have 6 electrons going into the reduction, so I'm going to need to take my aluminums and multiply them by 2, so we'll put those right into the coefficients. And my nitrogens, I don't really have to do anything to. There's going to be a 1 in front of each of the nitrogens. Now, this reaction is going to be done under basic conditions. So when we're under basic conditions, we're going to add OH minus to balance the charge on the left and the right. So what do I have for charge? I have 1 minus on the left. I have 2 minus on the right. So I'm going to go ahead and pop in 1 OH minus on the left. So now I have a net -2 on the left and a total of -2 on the right. So now let's see what I've got to do. Let's talk about the hydrogens. I've got 1 hydrogen on the left when I put in that hydroxide, and I have 3 hydrogens on the right. So it looks like I'm going to need to put some more hydrogen on the left. So let's go ahead and put in then an additional H2O on the left. So now I have 1, 3, and 3, so my hydrogens are okay. All right, now the oxygen should have just fallen right into place. So on the left-hand side, I have 1 O, 2 O's, 4 O's total on the left. 2 times 2 is 4 O's on the right, and I should be good. Let's just go ahead and double check. 1N, 1N, 2, 3, 4 O's, 4 O's, 2 AL's, 2 AL's. My total charge, let's see, I have 1 minus, 2 minus, so that's a total of 2 minus there, and 2 minus there. So this reaction is balanced under basic conditions. All right, hopefully with practice you'll see that this oxidation state change method is a bit more efficient than the half reaction method. But again, the half reaction method is going to have its bonuses when we talk about galvanic cells and some of the details that we have to put into that process. All right, so get to doing some practice, and so by the end of the next couple of days, hopefully you are an expert at providing balanced redox reactions.